Ever dug a hole and wondered what's really beneath your feet? Imagine digging past dirt, rocks, and worms, all the way to the center of the Earth. Our planet isn't just a solid ball of rock. It's built in layers, like a giant onion or a layered cake. Some layers are hard, some are gooey, and some are even liquid metal. A wild, hidden world right below us. We can't dig that deep, so scientists use earthquake waves to peek inside and map out what's there. Think of Earth like a hard-boiled egg, a thin shell, the crust, a soft white, the mantle, and a dense yolk, the core. These layers explain everything from mountain building to volcanic eruptions. Ready to peel back the layers and see what's really inside our planet? Let's start our journey. Scientists describe Earth's layers in two ways, by how they behave and by what they're made of. The first way is mechanical, how each layer acts. Is it hard and brittle, or soft and flowing? This helps us understand earthquakes, plate movement, and the planet's inner churn. The second way is chemical. What ingredients make up each layer? Is it light, fluffy rock or heavy metal? This tells us how Earth sorted itself when it formed. So when you hear about the crust, mantle, and core, or the lithosphere and asthenosphere, remember? They're just different ways to describe the same planet. Using both views gives scientists a complete picture of Earth's interior. Now let's look at how the layers behave. The mechanical layers. Get ready to meet the crust, mantle, and core in action. Here we go. At the very top is the crust, the thin, brittle shell we live on. It's like the skin of an apple, incredibly thin compared to the rest of the planet, but it's our home. The crust is broken into giant puzzle pieces called tectonic plates, which slowly move, crash, and slide past each other. These movements create mountains, valleys, and earthquakes. There are two types of crust: continental, thicker, lighter, made of granite, and oceanic, thinner, heavier, made of basalt. Oceanic crust sits lower, forming the ocean basins. Even though the crust feels solid, it's constantly being created, destroyed, and rearranged by forces below. Every mountain and earthquake is a reminder that our solid ground is always changing. The crust is Earth's crunchy, ever-shifting surface. It's fragile, dynamic, and the only part we ever see. Next, let's dig deeper into the mantle. Delving beneath the Earth's relatively thin crust, we encounter a vast and dynamic realm, the mantle. It's a world of immense pressures and temperatures, a place where rock behaves in ways that might seem impossible to us on the surface. This is Earth's thickest layer, making up about 84% of the planet's total volume. To put that in perspective, if the Earth were an apple, the mantle would be almost the entire apple, with the crust being just the thin skin. It's a truly massive part of our planet. The mantle isn't solid in the way we think of a rock, nor is it a liquid like water. Instead, it exists in a fascinating state, a solid that flows, albeit extremely slowly. Think of it like super thick taffy, or even silly putty left out for a long time. It's solid, but under immense pressure and over vast timescales, it can deform and move. This unique property is crucial to understanding many of Earth's geological processes. Over millions of years, its rock slowly bends and moves in a process called convection. This is similar to how water boils in a pot, but on a geological scale. Hotter, less dense material rises, while cooler, denser material sinks. Hot rock heated by the Earth's core rises slowly towards the surface. As it cools near the surface, it becomes denser and sinks back down. This slow, continuous dance of rising and sinking material drives the movement of the tectonic plates above. It's the engine that powers plate tectonics. The mantle isn't uniform. It has sublayers, each with its own distinct properties and characteristics. There's the rigid upper part, which is relatively cooler and more brittle. This upper part, along with the crust, forms the lithosphere, the Earth's outermost solid shell. Below the lithosphere lies the softer, more easily flowing asthenosphere. This is where the mantle's taffy-like properties are most evident. The lithosphere, broken into tectonic plates, essentially floats on the asthenosphere, like rafts on a slow-moving river. This allows the plates to drift, collide, and interact in ways that shape our planet's surface. Deeper still, the lower mantle experiences even higher temperatures and pressures, making it hotter and stiffer than the asthenosphere. Despite its stiffness, the lower mantle is still able to flow over geological timescales, contributing to the overall convection process. The mantle's slow churn is responsible for many of the dramatic geological events we see on Earth, including shaping continents, triggering volcanic eruptions as magma rises from the depths, and causing earthquakes as the plates grind against each other. So, the continents you see today, with their familiar shapes and positions, have traveled vast distances over millions of years, carried along by the mantle's powerful convection currents. The mantle is truly the engine room of our planet, the driving force behind so much of Earth's geological activity. It's always moving, always changing, constantly reshaping the world we live on. Now, with a greater understanding of the mantle's crucial role, let's journey even deeper and reach the Earth's core. Deep beneath our feet, past the crust and mantle, lies Earth's innermost layer, the core. It's a realm of extreme temperatures and pressures, a world unto itself hidden within our planet. This is where the story of our planet's energy begins, a story written in iron and fire. The core is essentially a giant metallic heart, a dense sphere composed mostly of iron and nickel. These elements, forged in the hearts of dying stars, sank to the center of our planet billions of years ago, creating this intensely hot and heavy core. But this metallic heart isn't a single uniform mass. The core has two distinct parts, each with its own unique properties and behavior. There's a liquid outer core, a sea of molten metal, and a solid inner core, a dense ball of iron and nickel under immense pressure. These two layers interact in fascinating ways, driving some of the most fundamental processes on our planet. The outer core is a swirling, churning ocean of molten metal, constantly in motion. This movement is driven by the immense heat rising from the inner core and the cooling effect of the mantle above. And when we say hot, we mean incredibly hot. The outer core reaches temperatures hotter than the surface of the sun, a truly mind-boggling figure. As this molten metal swirls and flows, it generates electric currents. These currents, in turn, create a powerful magnetic field that envelops the entire planet. This magnetic field acts as a shield, deflecting harmful solar radiation and protecting us from the constant bombardment of charged particles from the sun. Without it, life on Earth as we know it would be impossible. The inner core, though even hotter than the outer core, remains solid. This is because of the immense pressure at the Earth's center, squeezing the atoms so tightly together that they cannot move freely and remain in a solid state. The pressure is so intense that it overcomes the extreme heat. This solid ball of iron and nickel is surprisingly large, about the size of the moon, our celestial neighbor. And intriguingly, scientists believe that the inner core may spin at a slightly different speed than the rest of the planet, a phenomenon that is still not fully understood. The core's extreme heat and constant movement drive powerful forces that shape the Earth's surface, influencing everything from plate tectonics to volcanic activity. Without the core and its dynamic processes, we'd have no magnetic field, leaving our planet vulnerable. And with no magnetic field, we'd have no protection from the harsh radiation of space, making Earth a much less hospitable place. The core, therefore, is more than just a layer of the Earth. It's the planet's hidden engine, driving its internal processes and its shield, protecting it from the dangers of space. It's the final, fiery secret at Earth's center, a source of immense power and a key to understanding our planet's past, present, and future. But what exactly are these layers, the crust, the mantle, and the core, made of? What are their unique compositions and properties? Let's delve deeper and find out. Now let's embark on a journey to explore Earth's layers. We often think of the Earth as solid ground beneath our feet, but it's so much more than that. It's a dynamic, layered structure with distinct chemical compositions and physical properties. Understanding these layers is key to understanding how our planet works. We'll examine these layers by their ingredients, the chemical view. We'll delve into the specific elements and compounds that make up each layer, from the crust to the core. This chemical perspective provides valuable insights into the formation, evolution and behavior of our planet. When Earth formed, billions of years ago, it was a very different place than it is today. Imagine a molten ball of rock and metal swirling and churning in the early solar system. This primordial Earth was a hot, chaotic environment. Over time, as the Earth cooled, a remarkable process called differentiation occurred. Heavy metals like iron and nickel, being denser than other materials, sank towards the center of the Earth, gradually forming the core. This was a pivotal moment in Earth's history. Simultaneously, lighter rocks and minerals, less dense than the surrounding material, floated to the top, eventually solidifying to form the Earth's crust. This separation of materials based on density is fundamental to the structure of our planet. The crust, the outermost layer of the Earth, is primarily made of light elements. These elements are relatively abundant and play a crucial role in shaping the Earth's surface. One of the most abundant elements in the Earth's crust is silicon. It's a key component of many common minerals. Oxygen, another vital element, combines with silicon and other elements to form a wide variety of silicate minerals. And aluminum, a lightweight metal, also contributes significantly to the crust's composition. Continental crust, which underlies the continents, is thick and granitic in composition. Granite is a coarse-grained, intrusive igneous rock. In contrast, oceanic crust, found beneath the oceans, is thin and basaltic. Basalt is a fine-grained, extrusive igneous rock. Oceanic crust is denser than continental crust because of its higher concentration of iron. And magnesium, another relatively heavy element, also contributes to the density of oceanic crust. This difference in density is why continents rise higher than the ocean floor. The mantle, which lies beneath the crust, is significantly denser than both continental and oceanic crust. It's particularly rich in magnesium and iron, giving it a higher density compared to the crustal rocks above. The mantle is mostly composed of a rock called peridotite, an igneous rock composed mostly of the minerals olivine and pyroxene. This composition makes the mantle heavier than the crust. The immense pressure within the Earth allows the mantle to flow slowly over geological timescales. Deep within the Earth lies the core, which is almost entirely composed of metal. Iron is the dominant element in the core, making up the vast majority of its mass. However, a significant amount of nickel is also present, alloyed with the iron. The core is incredibly dense, far denser than the mantle or the crust. To illustrate just how dense the core is, a spoonful of core material would weigh significantly more than a similar volume of rock from the Earth's crust. The core's massive metallic composition is responsible for generating Earth's gravitational field, which keeps us grounded and holds our atmosphere in place. Furthermore, the movement of liquid iron in the outer core generates Earth's magnetic field, which shields us from harmful solar radiation. So as we move from the light rock of the crust to the heavy metal of the core, we see a clear trend in density. Earth is meticulously sorted by chemistry, with the lightest materials on the outside and the heaviest materials concentrated at the center. The unique composition of each layer dictates its physical properties, such as density, viscosity, and strength, which in turn influence how the layer behaves and interacts with other layers. But how do scientists determine the boundaries between these layers and understand their internal structure? The answer lies in studying seismic waves, which travel through the Earth and provide valuable information about its interior. Earth's layers don't blend smoothly, they have sharp boundaries, like secret handshakes. Scientists discovered these by studying how earthquake waves change speed or direction as they travel through the planet. The first big boundary is the moho, between the crust and mantle where rocks suddenly get denser. Next is the boundary between the lithosphere and asthenosphere, where rock goes from rigid to soft and flowing. This lets tectonic plates slide around, driving earthquakes and volcanoes. The deepest major boundary is the Gutenberg discontinuity between the mantle and the liquid outer core. Here, solid rock ends and liquid metal begin some earthquake waves can't even pass through. These boundaries reveal Earth's hidden structure. They're the keys to understanding our planet's restless interior. Why is the inner core solid, even though it's the hottest part? Why does the mantle flow? It's all about the battle between temperature and pressure. As you go deeper, both heat and pressure skyrocket. Heat tries to melt things. Pressure tries to keep them solid. In the outer core, heat wins. Iron and nickel melt. In the inner core, pressure wins. Metal stays solid despite the heat. This tug of war explains why Earth's layers behave so strangely. It's a world of extremes, shaped by forces deep inside. Why care about Earth's layers? Because what happens below shapes everything above. Earthquakes and volcanoes are direct results of the crust and mantle in motion. Studying the layers helps us predict disasters and build safer communities. The layers also give us resources, geothermal energy, metals, and minerals, all formed deep inside. Most importantly, the core's magnetic field shields us from deadly solar radiation. Without it, Earth would be lifeless, like Mars. So next time you stand on solid ground, remember, a powerful hidden world is churning beneath your feet. Our planet's layers make life possible and keep our world in motion.